And with that, I wish you a very enjoyable and informative session. Over to you, Yashar.
Thank you very much, Tim. As Tim mentioned, my name is Yashar. I'm an associate professor at Rotterdam School of Management. And I'm very pleased to be the chair of this session. My research interests are mainly at the moment focused on mechanism design and tariff mechanism designs for different levels of energy systems, including peer-to-peer, residential setting, all the way to wholesale electricity markets. As such, I see that this session is very interesting and very diverse, because I see that we are including all different layers in one session. We have transactive energy, peer-to-peer, residential setting, and also wholesale market. As also Tim mentioned, and to be fair to all the presenters, I try to be very strict with the timing. So I would like to ask the speakers to stick with the timeline. And if there are further questions, of course, you can still continue discussion on the Slack channels. And I'll try to accommodate as many questions as possible during the sessions. So without further ado, I would like to start with introducing the first speaker, Dr. Qing Yang. He's an assistant professor at Shenzhen University. He's also a principal researcher in the Blockchain Technology Research Center of Shenzhen University. His research interests include blockchain technology, intelligent energy in smart grids, and IoT networking. So Qing, if you're here, please start sharing your screen and the stage is yours.
Oh, sorry. My name is Qing Yang, and I'm from Shenzhen University. Today, I'm going to present our work titled Blockchain for Transactive Energy Management of Distributed Energy Resources in Smart Grid. And this is a joint work with Professor Wang from Monash University and Professor Wu, Professor Wang, and Professor Zhang from Shenzhen University. Okay, in my talk, I will first introduce the background of distributed energy resource in smart grid. And then I will describe our system model and the problem formulation. Then I will discuss our algorithm design, and followed by system implementation and evaluation. And last, I will summarize our paper. Okay, so this figure shows a typical smart house setup. So in this smart house, we focus on the distributed energy resources. That includes, for example, the renewable energy generators such as solar panels and wind turbines. And we also consider different kinds of electric appliances. And since now the battery energy storage system is becoming popular, for example, the Tesla Powerwall as shown in this figure. So we also consider battery in our system. And finally, there's a smart meter that connects all of these components into the local smart grid. Okay, now with the penetration of DER into our modern life, it poses a lot of changes to our current power system. For example, we will meet complicated DER management algorithms, and we will always see that the renewable energy is not fully utilized. And we also face a lot of privacy leakage issues. And in this work, we consider a scenario for virtual power plant. Of course, we can also consider other scenarios, but we just take the VPP as an example to illustrate our method. So in a virtual power plant, a smart house can be regarded as a prosumer since it can not only consume electricity from the grid, but it also can produce electricity with its own renewable energy generators. Here we let U denote the set of prosumers, and we let T denote the operational horizon. Here we consider 1 hour plot, 1 hour slot. So we divide each day into 24 slots. Okay, this figure illustrates the power supply model in our virtual power plant. If we look at a single smart house, actually it can draw energy from two sources. One is from grid. So here we let GUT denote the power supply that the prosumer draw from the grid. And also it can generate energy by its own renewable energy generators. So we let RU to denote the renewable energy. And so the prosumer's cost of the grid supply consists of two parts. So because the renewable energy is free for himself, so he can only need to pay in the grid for the grid supply. Here we assume a two-part tariff billing scheme, which is quite normal now. So we have normal price alpha and peak price beta. So the total cost of prosumer's grid supply can be written in this equation. Okay, and this figure will show the cost of the prosumer's electric appliances, which can be divided into two kinds. The first kind is the flexible appliances, which can be shifted in time. For example, the washer, the dryer. The prosumer can arrange this kind of loads with his own preference in time. And another type of appliances is the inflexible appliances, which cannot be shifted in time. For example, the refrigerator or the lighting system. And here we denote the prosumer's discomfort cost in this equation. And here this LU reference T denotes the prosumer's preferred schedule, since every prosumer have preferred schedule. And actually this cost is a derivation from his own preferred schedule. And here we also consider P2P energy trading. And this is a typical P2P trading setup. We denote the prosumer's trading cost in this equation. And we also consider the cost of the battery, since charging and discharging of the battery will degrade the lifespan of the battery. So we denote the prosumer's battery cost in this equation. So this is proportional to the charging and discharging amount of the battery. And finally, we assume the VPP provide an ancillary service to the grid, which means the VPP can dispatch energy back into the grid to stabilize the grid operation. So the grid operator will pay a reward to the prosumer if the prosumer provide ancillary service. So here pi AST is the reward price of the ancillary service, and this price is adjustable. So the grid operator can adjust this value to adjust the amount of ancillary service from the VPP. So finally, we get the problem of our paper. So for a single prosumer, its cost is the summation of the cost of different components minus the reward of the ancillary service. And for the whole system, our optimization target is to minimize the overall cost of the system. So we denote the transactive energy management problem in this optimization equation. And the result, the output of the optimization problem is the optimal DER schedule for all the prosumers. So conventionally, how do we solve this problem? Actually, in conventional method, we usually employ a central coordinator to solve this optimization problem. Usually, the grid operator is the central coordinator, it will connect the information from all the prosumers and solve the optimization problem in the central node. However, this method has several drawbacks. First, it has a single point failure, right? It has a risk of single point failure. And second, the operation inside the grid operator is just a black box to all the prosumers, which causes a trust issue. And the third, since to solve this problem, the operator have to collect all the privacy information from prosumers, so it also causes privacy leakage. And finally, maintaining a central coordinator needs a very high maintenance cost. In this paper, our method is we employ the blockchain platform as the upper layer solver, and we use the ADM method to decompose this optimization into a primal problem and dual problem. So the primal problem and dual problem, we can solve it in an iterative manner. And here we describe our algorithm design. First, why we use blockchain in our system? Because blockchain can benefit us with this three benefits. First, blockchain is a trusted computing platform. Second, blockchain has a very low maintenance cost since it's a P2P system. Third, blockchain provides a very convenient online payment tool. So we can pay, for example, P2P trading or ancillary service reward just using the token inside the blockchain. And in our system design, we solve the primal problem by the prosumer locally, and we solve the dual problem using smart contract on the blockchain. Using this method, we preserve the prosumer's private information within the smart house, and also we remove the need for a central node. And the smart contract can output verifiable and trusted computer results. This is the detailed algorithm in our paper. So in the first stage of our algorithm is parameter initialization. We initialize all the parameters such as the convergence thread and initial parameters for the ADMM. And then we let each prosumer to solve the primal problem locally. Here we just use the quadratic programming library from Octave to write our code to solve this problem, because this is a very typical convex optimization problem here. And then when all the prosumer finish his primal problem, it will update the smart contract, and smart contract will run to solve the dual problem. Here we implement this part of algorithm in Solidity and pre-compiled contracts. And this algorithm will iterate until the convergence thread is met. And the output of the algorithm will be the optimal schedule, energy schedule for all the prosumers. And in our system design, we run the blockchain node in smart meters. So, and then we implement the blockchain software based on the source code of Ethereum, which is a very popular open source blockchain project. And in this work, we adopt the POA consensus protocol rather than POW, because POA is more feasible on IoT devices such as smart meter. So here we have a validator node and normal node. And this figure shows the architecture of the blockchain. And to evaluate the algorithm, we build a small network of IoT devices. So here we use a NanoPi Neo 2. So this is a very nice little device. It has a screen, and it has Ethernet interface, and it has an ARM CPU with 4 cores and 1 GB memory and 6 GB storage. We use this device because this is quite close to a typical smart meter setup. And this figure shows the test network of our evaluation system consisting of 48 nanopis. And we measure the resource consumption of running a blockchain node on this device, and shows in this table. We think this is feasible. Okay, and this is some preliminary results of our evaluation. In Figure A, we shows the confirmation delay. So we measure the transaction confirmation delay with different number of validators, with 5, 10, and 20. And the result is all of them are about 76 milliseconds. So this is very fast. And in Figure B, we test the throughput of our blockchain system. We also increase the transaction rate. The emitting rate of the transaction from 5 to 200, and we measure the confirmed transactions in the network. And we found that the TPS, the throughput will saturate at 150 TPS. So this is also viable for our system. And this figure shows the result of our transactive energy management algorithm. In this part, we use MATLAB simulation rather than experiment. In this simulation, we use data collected from real world in Hong Kong, including regenerable energy system data and electric appliance data. And we simulate 10 prosumers during 1 week. And this figure shows active energy trading among prosumers. We also have other results, but due to the limit of paper, we only show this figure. Actually, in the full results, we can see optimal transactive energy management is achieved by our algorithm. Okay, let me conclude the paper. In this paper, we present a blockchain-based transactive energy management system for DER, and we designed a decentralized optimization algorithm, and we implemented in a real blockchain system with a test network and real-world data. And during the investigation of this paper, we also found several drawbacks of current system. So in the future, we're going to investigate decentralized algorithm with lower complexity, since currently the complexity of algorithm is quite high. And then we also will investigate high-performance blockchain for IoT devices, because 150 TPS actually is not enough for large-scale network. And finally, we'll consider large scale of smart grid network rather than small scale. Okay, this is the end of my presentation. Thank you for your attendance.
Okay, thank you very much, Qing. Indeed, very interesting talk and presentation. I'm looking at the Slack channel and I see Keshav actually has 2 questions. So Keshav, if you can unmute yourself and speak up, that would be easier.
Yeah. Sure, thanks, yeah, sure. Thanks for the talk. I had 2 questions. So one was, how do you ensure that the participants, that is the smart meters, do not lie, that they don't misreport what they want? And second, what is the value of the blockchain over and above just the standard broadcast of the smart meter values?
Okay, so your first question is about how do I ensure that the prosumer will report his true result, right?
Yeah.
Actually, this part is guaranteed by the optimization, by the design of the algorithm.
I see.
Okay, let me show you this figure. So if you look at this optimization target, actually this total cost include the cost of every prosumer. Right. So if every prosumer report his true result, then actually this is the best strategy for that. For each prosumer. If he didn't report, his true intention or his true result, actually he gained nothing, right?
No, you're minimizing the sum of the costs, but it could be that I have an incentive to misreport my cost and then get a lower overall cost for myself. It may increase the cost of somebody else. So you haven't shown incentive compatibility with this expression. This is just showing social welfare.
Right. The question, notice that
sorry,
here.
Sorry, Qing, can I just quickly answer this? I'm Wang from Monash University and co-author of this paper, and thanks to Keshav for this question. I think to be short, that this whole kind of framework that does not guarantee that of misreport of untruthful report of the user's kind of energy profile or cost, because I think kind of a better mechanism design here probably be something as a future work to guarantee the truthful report through some kind of market mechanism. Yeah, thank you.
Right, yeah, because what you're doing here is just doing social welfare optimization and then decomposing that into a two-part ADMM.
Yeah, it's just a distributed algorithm, indeed.
Right, got it. Okay, and then the other question was, what is the value of a blockchain over just the broadcast?
So it's about the blockchain in broadcast, or?
No, I mean, you're using the blockchain SSC here as a replacement for broadcast, which is what you would do with ADMM, right?
I think that is only just one function. I think more importantly, we use blockchain to solve the dual problem in smart contract.
No, but why would you want to use a smart contract as opposed to just a regular distributed algorithm?
See, if you, I mean, if you use, usually we use a server to solve the dual problem, since this dual problem is just like it's like a upper layer problem.
Yes.
By doing this, we need another trusted central node, right?
No, the dual problem doesn't. No. Why does the dual problem need a trusted central node?
Because you must guarantee that the output of this dual problem is correct and verifiable to all the prosumers. Otherwise, if you use, for example, if you use the central node to solve this dual problem, then it's another black box to the prosumers, right? Because the prosumers cannot believe that the central node will solve the dual problem in this equation in a correct way, right?
Okay, I see. Okay. I guess let's take this offline, because I have to look at the structure of the problem more closely, and I'll take a look at your paper. Thank you.
Okay, thank you.
Okay, I see that Robert wants to also ask a question, but Robert, if you don't mind, can you ask a question on the Slack channel, because we are already over time, and I also have some other questions, so I will also post it on Slack channel. And just to be fair to the other presenters and for the interest of time, I would like to move on to